the domain and the range of the inverse trig functions were, right? Because two functions that are inverses of each other, their domains and their ranges switch, flip-flop. So these are the graphs of the inverse trig functions, and you can see that the domain corresponds to the ranges that we listed above, and then the range of each of the inverse trig functions corresponds to the domains that we had restricted above. Okay, so we're going to kind of reference these. You will not have to graph these by hand, okay? But I have the graphs here for us to kind of reference because we are going to derive the derivatives of the inverse trig functions. Okay, also taking a step back to like thinking when you were first introduced to inverse functions, like inverse algebraic functions. They had to be one-to-one. If a function was one-to-one, you're like, oh, it has an inverse. What did you do? What was the process for finding the equation of an inverse function? What did you have to do?
Reverse your steps. Reverse the y.
Switch the x and the y. So like if we're thinking about the graph of sine and we're like, we've restricted the domain so that it's a one-to-one function, it has an inverse. If we were thinking about finding the inverse of sine, we would switch the x and the y. And then this is actually something that you guys know how to differentiate. Use a little implicit differentiation. Okay, thinking chain rule. So sine is the outside function, y is the inside function. The derivative of sine would be cosine. Leave the inside alone, and then times the derivative of the inside would be dy over dx. And the derivative of x with respect to x would be 1. Okay, so from here, notice that dy over dx is 1 over cosine of y. This is the derivative, but it's kind of funky because in order to determine what the slope of the tangent line would be, you would be plugging in the value for y instead of x. Now, one alternative or an equivalent form of this derivative could be thinking about replacing y, because what is y equal to? Arcsine of x. So one form that we could write this in is dy over dx is equal to 1 over cosine of arcsine of x. Do you guys remember how we would rewrite expressions like this in their equivalent algebraic form last year?
I
Remember that?
don't remember how to do it though.
Okay, so we had covered, and we're going to do the exact same thing. How you can rewrite, remember this is y. This represents an angle, right? Arcsine of x represents y. We know that up here, sine of y is equal to x. So going off of that to make a picture, and I'm going to write x as x over 1. Thinking back to good old SOHCAHTOA, sine is what ratio? Yeah, opposite over hypotenuse. If this is the angle y, opposite hypotenuse. And we could figure out what this leg would be by using our handy dandy Pythagorean theorem. A squared plus x squared is equal to 1 squared. So a would be equal to the square root of 1 minus x squared. So then we're trying to figure out how to replace cosine of y. Right? We want to replace cosine of y in terms of x. Cosine of y, cosine is adjacent over hypotenuse. So that would be the square root of 1 minus x squared over 1. So another way that dy over dx can be rewritten would be as 1 over the square root of 1 minus x squared. And this is how we most commonly think about the derivative of arcsine. And this is the formula that I would give you for your assessments. But all three of these statements technically represent dy over dx for our cosine.
Like, how did you get to the 1 over the root of 1?
Because I was just replacing cosine of y. Did you follow how I came up with cosine of y?
Yes.
So we thought about going like replacing that to get us there. Okay, why don't you try using this as kind of your model? Why don't you come up with the derivative of arc cosine? And if you're stuck, you can talk to someone sitting near you. Oops.
Why did you reverse this here?
So this technically represents inverse sine. Because if we're thinking about sine being y equals to sine of x,
I see.
inverse sine could be written as sine of y. It's kind of like how we have the two different forms for log and exponential
Yeah.
form of like the inverse of an exponential function. How's it going, you guys? Do we need another minute, you guys? Do we have any interesting observations?
Can I just run to the restroom?
You can. Should we check in? Did we just get the opposite of the derivative of arc sine? Yeah. Okay. Again, we have three different ways that the derivative of arc cosine can be represented. This algebraic form is what we tend to think of when we think about the derivative of arc cosine, and it's just the opposite of the derivative of arc sine. Exciting stuff, right? Okay. Does it say, can we do the derivative of arctan? Are we ready for it? You know how much I love that response. It sounds so sincere. Okay, so let's first rewrite arctan as tangent of y is equal to x using implicit differentiation. D over dx of tangent of y equals d over dx of x. Okay, so thinking chain rule, derivative of tangent will be secant squared of y and then times dy over dx equals to 1. So dy over dx is 1 over secant squared of y. Okay, that's one representation of the derivative. You could also, just to get it so that dy over dx is a function of x, you could substitute arctan of x in for y. That's one option. But you will more commonly see this derivative represented in the algebraic form, and we can get there the same way that we did drawing a right triangle before. That look like a right triangle? Okay, so thinking about SOHCAHTOA, tangent of y equals to x over 1. Tangent is opposite over adjacent for labeling our triangle. So x1, which means the hypotenuse would be the square root of 1 plus x squared. You did a little Pythagorean theorem. And since we are trying to replace secant squared of y, right? Secant squared of y is what we're trying to replace. That's the same as secant of y squared. Okay, so secant is the reciprocal of cosine. Since cosine is adjacent over hypotenuse, secant will be hypotenuse over adjacent. So the square root of 1 plus x squared over 1. And since that's being squared, that's just 1 plus x squared. Now, part of the reason that we are referencing the algebraic form of these derivatives is for section 5.8, we're not learning how to integrate the inverse trig functions, but we're using the reverse of these differentiation formulas. So it'll allow us to integrate some functions that like a u sub wouldn't work. But if you recognize, oh hey, the antiderivative of this expression would be like arctan or arcsine. Okay, in the same way, because we would be using the same approach, right, for finding the derivative of arc cotangent. I'm going to give you a little spoiler. The derivative of arc cotangent is just the opposite of the derivative of arctan. In the same way that the derivative of arc cosine was just the opposite of the derivative of arc sine, right? Gabby, not nap time in here. Killing my vibe. No killing vibes. We can sit up at least, right? No nap time. Or go in the closet. Okay. So I'm going to leave this one for you. If you feel like you want to go back and try deriving it, you can. Maybe as a little review for your test. But let's take a peek at the derivative of arc secant together, just because it's the same process, but there's one little extra piece to consider whenever coming up with the derivative of arc secant. Sprinkle? We'll sprinkle. I don't know if I follow. Cool. All right, so rewriting y equals arc secant of x as secant of y equals 2x. Okay, this is the same thing we've been doing, using implicit differentiation. What's the derivative of secant, you guys? Secant times tangent, yeah. So this will be secant y tan y times dy over dx equals 1. So dy over dx will be 1 over secant of y tan y. Okay. And the other form, like if we just wanted to pop arc secant in there, we would have dy over dx equals 1 over secant of arc secant of x. And tangent of arc secant of x. Okay, and then in the same way that we did before, we want to rewrite that in the algebraic form.
Isn't secant of arc secant just...
Let's talk, that's what we're about to talk about. Is it?
Maybe.
We'll talk, maybe. So that's the little extra sprinkle that we're about to talk about. But yes, Billy, that sort of, kind of simplifies to x. Okay, so if we take, am I going too fast? Do I need to slow down? Okay, so if we take secant of y equals to x over 1, okay, secant would be the reciprocal of cosine, so that would be hypotenuse over adjacent. Did I label my angle in these? I didn't. need to label the angle. Okay, so then this side would be the square root of x squared minus 1. Here's the thing. I'm going to show you two different reasons for this. Okay, one reason that I'm about to do what I'm about to do is thinking about the domain of arc secant. It would be the range of secant, which would be negative infinity to negative 1, union 1 to infinity. So x can be positive or negative. If we were thinking about an angle like in the xy plane, or even if we're just thinking about the side lengths of triangles, right? Shouldn't x be positive? Like if we're thinking of x as representing the hypotenuse of a triangle, x should be positive. But based on the domain of arc secant, right? Because it's this x, based on the domain of arc secant, x could technically be negative. So to resolve that issue, what have we done in the past? We're going to slap some absolute value bars on there. Which means that secant of y can be replaced with absolute value of x. And then for tangent of y, that would be opposite over adjacent. So tangent of y will be the square root of x squared minus 1. Now kind of my other justification is if we didn't put those absolute value bars, like let's say that we just let this simplify to x, then if we were inputting values that are in the domain of arc secant, couldn't your derivative dy over dx be either positive or negative depending on the sign of x? Remember though, this is an inverse function. It's a continuous inverse function. Do you remember what I said about continuous inverse functions? Can they be both increasing and decreasing? No, they can't. They're monotonic. If we look at the graph of arc secant, notice that arc secant is increasing everywhere. Therefore, dy over dx should be positive over its entire domain. Yeah, so we need those absolute value bars there. Okay, so this is how we typically think about the derivative of arc secant, although all three of these statements represent the derivative. And another spoiler alert, the derivative of arc cosecant is just the opposite of the derivative of arc secant. Which is kind of nice from a memorization perspective, right? Because you really only have 3 derivatives to memorize or to recognize. And then you know, and remember how for the derivatives of the trig functions, my way of like keeping which one is positive and negative straight in my head is the ones that start with C have negative derivatives. Well, looky, the derivatives of arc cosine, arc cotangent, arc cosecant are also all negative. These are ones, again, I'm going to give you these formulas like the week before your actual AP exam with the College Board is when I would probably really study them to make sure you know them. I think you'll be familiar with them at that point, but that's maybe when you want to, if you're like a flashcard person or something, like want to try try and have this.
They don't give you those, right?
They do not give you this.
Is it better to like memorize them or to memorize how to derive them?
That's up to you. I would be familiar with them. I would at least like have some you know what I'm trying to say. Can't say it right now. COVID, you know, fog brain. Where am I going with this? Oh, but then like if you needed to confirm, you could quickly do a little derivation to be like, oh yeah, it's that one. Does that make sense? That's what I would do. I were you. Okay. So you guys, why don't we use these formulas? So if we want to differentiate arc sine of 4x, we have to use a little chain rule. Okay, so thinking about derivative of arc sine. Derivative of arc sine would be 1 over the square root of 1 minus, leave the inside alone, and then times the derivative of the inside would be times 4. That would be the free response answer, but you always could clean that up a little bit. Oops. Why don't you try the next one? Derivative of arctan of the square root of x. Again, thinking chain rule. One common mistake, and I only started, I think it's because the way the chapters, like since we're in the same chapter still as like exponential and log functions, a really common mistake that I'll see is people are like, oh, I can plug. It's not a logarithm. Don't try and plug arctan. You can't do it. Okay, remember log properties, plugging is only for logarithms.
Now I really know what
Now you do. It didn't occur to you before. I'm telling you, every year. So always people who try and plug the inverse trig functions. All right, let's do one more. What time are we out of class? Oh my God, we have so much time, you guys. I thought we were out in the next like couple minutes. Wow. No. How was Doc's thing yesterday?
How was what? Oh,
Doc's thing.
it was good. He just gave like a 30-minute speech to these like old people, and we just sat and
Where
ate.
was it?
It was in Burlingame.
Whoa.
Was it like a Hall of Fame type thing?
Yeah, well, there was maybe like 30 people there. So yeah.
No, I know, but what was it for? Like their like Hall of, isn't he from Burlingame?
Yeah. So he's like went like his dad like one of the founders of it or something like that.
Of what?
Of the Rotary Club, which is
Oh.
or I don't know one of the founders, but he had something involved with the Rotary Club. So
What is a Rotary Club?
I have no idea. Apparently, it's a really big.
Is it like a
Not really
moose
attended
club?
it.
Is like a moose or a elk? Rotary? What's Rotary What's a rotary?
It's like a rotary phone. It's
That's what I was
rotary.
thinking.
But I don't know if it means rotary, like rotary.
Can we look up rotary?
I have a rotary phone.
Apparently rotary
Yes,
club international
I had
is
a
like
rot-
this really big thing,
I had a rotary phone.
but I don't know if that, yeah, I don't know.
It's a community, Rotary International is a global network of 1.4 million members who volunteer their time and resources to address community needs and focus on peace, fighting disease, and promoting ethical standards in all vocations. So these clubs,
Is that related to
I don't really know what they do.
Like, he was just talking about like our team this year and like leadership and like how he coaches people and stuff.
Oh, it does say Club of Los Altos for some reason on the first photos. I don't know why it's Los Altos.
Yeah.
Sounds fancy.
Oh, there's like
Yeah, we
a
went
chapter
to-
in all those. Oh, it's giving me Los Altos results.
You actually sound just like your sister.
Really?
Like the exact same.
Really? Oh my god.
And that too when you say it.
Okay.
Your siblings talking about the same.
You guys, this one is like double inception, chain rule in chain rule. Okay, so derivative of arcsecant, we're like 1 over absolute value of e to the 2x times the square root of e to the 2x squared minus 1, and then times the derivative of e to the 2x, which requires chain rule again. It's kind of fun, huh? Now, are these absolute value bars actually needed?
Hello. That's crazy.
Are these absolute value bars actually needed?
No.
No, because
Is not
It doesn't be negative.
it doesn't be negative. Isha quote, it doesn't be negative. Okay, which means we can cancel those puppies. And then we'll have 2 over the square root of e to the 4x minus 1. It doesn't be negative.
Yeah.
You forgot I was here. Hello.
But this really, it doesn't.
I did too. Or what's going on? You do normally talk.
Fire who?
You do normally talk. Are you tired?
Do you have a rough afternoon?
You have a rough afternoon? Why?
Calc and Calc.
Ooh.
I have a day from 8.
I had lang Spanish, then this, then
Wow, that is.
Oh.
Empathetic.
Hashtag never catch a break.
But then tomorrow's easy, right?
Yeah, I feel
You are the go.
I still have to wait easy.
You can't have 4.
Oh, wait, no.
All right, you guys, let's do one more and then we'll be caught up to at least one of the classes. Let's find the equation of the tangent line. So we'll have a couple more examples to go through at the beginning of next class, but we've gotten through enough where you should be able to complete the homework. Find the equation of the tangent line in the graph. Go ahead and try this. Equation of a tangent line, we need a point and a slope.
Oh. Okay.
How far did my class get?
You're Leo. Are you all the juniors? You're all the juniors. Did not get to this one. So you are caught up.
Oh, yeah, nice.
Hello.
She's sitting where you
I think it's
are.
all late for that question to be asked.
Sorry, wait, I asked if anyone sat here.
No, but were you guys in the same class last semester? Michael.
She was in like.
No, I was in their class, yeah. Well, last year, maybe.
I don't know.
Wait, what class? We're in here in office hours sometimes together. Maybe that's why. I don't know.
That's why the seating was weird.
Crawl is mid most of class.
You guys, what's inverse cotangent of 1? Remember, inverse.
Pi over 4.
Remember, the inverse trig function of any positive ratio will be an angle from Q1. All of the ranges include quadrant 1.
I was gonna
Never
say
knew
that.
that. Angry math. Wait, how is it pi over 4?
Because it's the inverse cotangent of positive 1. So if you're thinking about the range of inverse cotangent, it's from 0 to pi over 2, union pi over 2 to pi. Wait, no. Is it just 0 to pi? It's just 0 to pi. It's just 0 to pi. So we're thinking from 0 to pi, what angle would make cotangent equal to 1? And since it's a positive ratio, you're thinking Q1 angle. So what Q1 angle on the unit circle would make cotangent equal to 1? Julie,
Can you show us how you write pi again?
how I write pi?
Yeah, because I've been doing it like this.
For pi day, I don't write pi right. I write pi like somebody I saw write. One of my professors or something wrote pi. I don't think I write pi in the correct way.
How are you supposed
How are you supposed to write
Wait, how do I write it?
But no one writes it like that, cause
I think I write it like that.
Yeah.
But like I think you're supposed to write it like that.
No, because I do
Yeah.
a line and then two
That's how I read it.
No, like-
I ain't got time for 3 lines. I need 2-liners.
Well, that's.
I just
read
do
it.
down,
One
straight,
line and then
straight,
one side.
straight.
Like that.
No, but that looks
I do
That's
this.
what she does.
I don't know what that looks like.
No, it's this.
That
Yeah,
looks
I
like
know.
yeah.
I was looking at it. I was just like, why does this look like 6? Why does it look like 6?
No,
Stop
but
it,
if you
please.
make it squiggly, then it doesn't. But yours isn't squiggly.
Okay, and then we need this
I thought that was squiggly, okay?
the slope.
Like,
That's so sad.
like,
I like that one.
Stop.
tell me that.
Stop flirting, you.
What?
Huh?
I want to see you no more.
Oh, playing today.
Da-ding.
That's crazy. Even more of a I love my sport.
Wait, isn't it negative?
What negative? Oh, good point. I was making sure you're paying attention.
What?
The negative.
It's arc
It's negative? Oh.
cotangent, derivative of arc cotangent. I forgot the negative. Okay, you guys can start your homework and we'll wrap up these last few examples next time. To which one? To this?
Yeah.
Oh.
Hold on.